Greetings, colleagues. Welcome to SAMPE's Technical Committee webinar on Ablation Science and Technology for Aerospace and Defense Applications. My name is Raj Manchanda, and I'm the Chief Technology Officer for SAMPE. Again, welcome to the SAMPE Technical Committee webinar on Ablation Science and Technology for Aerospace and Defense Applications. In the chat, please go ahead and start to enter in your name, your company name, your job title, and where you are geographically located. Once again, in the chat, please introduce yourself with your name, your job title, your company name, and where you're located. We're very pleased to have Robert Brushhaber with us as moderator. Robert is the Director of Engineering at Texas Research Institute, Austin. Robert is also on SAMPE's Global Board. Robert is also past chair of SAMPE's Technical Excellence Committee and very active in SAMPE. I will pass over the mic to Robert, and he can introduce our esteemed speaker, Dr. Joseph Koo. Thank you, Robert.
Yes, before we begin, I would like to introduce our esteemed speaker, Dr. Joe Koo. With over 49 years of experience in both industrial and academic settings, Dr. Koo is a highly respected figure in research and engineering management. He currently serves as Senior Research Scientist, Research Professor, and Director of the Polymer Nanocomposites Technology Lab in the Walker Mechanical Engineering Department at the University of Texas at Austin. Dr. Koo is also the founder of Koo & Associates International, where he holds the position of Vice President and Chief Technology Officer. He is a fellow of SAMPE. Additionally, he serves as an associate editor and advisory board member for several international journals and societies, including the SAMPE Journal. Dr. Koo's experience lies in polymer nanocomposites, including their processing, characterization, and applications. His work spans a wide range of areas such as thermal protection systems, solid rocket motors, additive manufacturing, flame retardant polymers, fire-resistant fabrics, thermally conductive composites, and advanced sensor technologies. He is also well versed in modeling polymer degradation, material response ablation, 3D microstructure analysis, and CFD flow field modeling. Dr. Koo authored 4 textbooks and over 700 papers and presentations in fields of materials, thermal, and optical sciences. His forthcoming book, Ablation Science and Technology, will be published by the Cambridge University Press in 2025. I've personally known Dr. Koo for 20 years and met him at my first SAMPE conference. I consider him a colleague, a friend, and a mentor. He inspired me to return to school and pursue my master's degree. The students in the Koo Research Group at the University of Texas at Austin have been exceptionally fortunate to benefit from Dr. Koo's mentorship. Under his guidance, they have not only gained profound knowledge in the field of ablation and polymer nanocomposites, but have also developed critical thinking and innovative problem-solving skills. Dr. Koo's dedication to his students' growth is evident in the way he fosters a collaborative and intellectually stimulating environment, encouraging them to push the boundaries of their research. Many of his students have gone on to achieve remarkable success in their careers, contributing significantly to both academia and industry. They have published influential papers, presented at SAMPE conferences, and received numerous SAMPE awards for their outstanding work. Dr. Koo's mentorship has been instrumental in shaping these students into the next generation of leaders and innovators in material science and engineering. His commitment to their development is a testament to his passion for education and his unwavering support for his students' aspirations. At the end of this webinar, do not forget to answer a few survey questions to help SAMPE out. Please join me in welcoming Dr. Koo.
Well,
Thank you so much, Robert.
Okay, Robert, thank you for the lengthy introduction. I have been a SAMPE member for a long time, and I encourage all of you to actively involve in SAMPE conference, CAMEX, as well as actually in the SAMPE journal. Okay, so what I want to do is to go over selective areas that we have been working on ablation science and technology for aerospace and defense application. So I'm going to actually go over my lecture outline. I tell you a little bit about what's ablation and tell you a little bit about processing and fabrication and how you actually do a thermal property characterization using different type of instruments in our lab. and I'll move on to aerothermal testing. And within that particular area, I'll explain to you what is OTB and other instruments that we use. I also will introduce you to thermophysical and mechanical property characterization. These are very important. I think I actually use this exactly the same route that we have been designing material, analyzing material, as well as actually doing the microstructure modeling, and last not the least, talk about material response modeling. And eventually I'll give you a summary and conclusion. Okay, so first of all, I have two slides telling you what is ablation. If you actually go into the dictionary, you find out ablation actually defined is surgically remove or loss of a part. I think when it first came in the dictionary, it's mostly talk about thermal process of removal of snow and ice from an iceberg or glacier. But right now, there are actually two type of, if you do a Google and what is ablation science, you could actually see laser ablation and thermal protection system ablation, TPS. I'm going to concentrate on TPS ablation, and I'm going to briefly talk about what is actually laser ablation is mostly to do in the medical field, have to do with LASIK and all these and actually have been around for a long time. Another area that you could see laser ablation is in the clothing and actually fabric industry. They use it to cut the fabric so the fabric will not be fraying. Okay. Well, I'm only concentrating in this seminar, and that's my area expertise. It's ablation for thermal protection system as well as for rocket motor. Probably everybody knows in World War II, there's a German V2 actually like missiles. That is actually was first started to have the demand for ablative material. I think these projects started the space program around the world, and they're actually been used for TPS as well as for other applications. And I'm going to name a few of those for reentry vehicles, rocket nozzle, and also insulation for propulsion system. And these are the ones that actually been used, ablative material used in this kind of industry. And over all these years, there actually have been extensive amount of research conducting on ablative material testing and sensing, ablative material characterization, and numerical modeling. And all these are actually very different areas that I will probably go actually over. And these are all interconnected. It's not just one area. Okay, I'm going to show you what we are actually doing in the Cool Research group. This actually paper, I wrote it and actually submitted to SAMP Journal in actually in 2024. It will give you a lot of information in the open literature. So I'm going to go over this actually approach a little bit in detail. First, we will process and fabricate these TPS material or ablative material. And we will actually do a first screening of these, and we call it thermal characterization. That's what we use some of these actually instruments, and we will actually loop back later on doing characterization for thermal properties of virgin and char. Why is it important? Because eventually all these will be input into actually the modeling. And after we done some of these, we use it as screening. And afterwards, we will actually do aerothermal testing. We actually, in our lab, we have very low cost oxyacetylene test bed. We don't just blast material. We actually do a fair amount of what I call advanced diagnostics. And eventually, you will go to actually NASA's high net arc jet or actually AEDC arc jet. But those are very expensive and also a long lead time. So another area that I actually will discuss a little bit is microstructure analysis. We need to know the mechanism of how these materials were actually performing well. We have done a fair amount of SCM, and actually 3 years ago, we start actually doing synchrotron micro CT analysis in Berkeley, actually National Laboratory. Some of these data we will be actually using and calculate the properties based on micro CT data. Okay. The last not the least that we will actually do modeling. We will do actually like CFD modeling. We'll do actually thermodynamics, actually transport calculation, and these will actually provide the surface response of these materials, and we'll fit all these into ablation modeling, and these are computer code we actually use in our group. Why is it important? If you actually start develop material, you never actually go through this process. You are always testing material, but the designer will going to come back and ask you, well, how thick the material? What are my prediction? That's why we actually do a fair amount of material response modeling. I'm going to today, I'm actually going to go through this post and the approach we're using, and we're using this in a lot of projects. And I'll give you some examples. So the very first thing I'm going to talk about is processing and fabrication, because we are examining all these new materials, not just the traditional one. So I'm going to give you 3 examples. The very first one that we have been processed and fabricate carbon UHDL, which is a resin system that we've been working on with a polysiloxane. So these are the we'll use hot melt, we'll actually use molding compound and compress all these into carbon UHDL molding compound materials. So that is one way that we will process and fabricate carbon UHDL, the same thing as carbon phenolic. We will actually use a fair amount of those in our lab. The next one is we actually start using what you call dual layer TPS. And that is actually part of my students' thesis. And we will actually examine different layer on the right-hand side. We have 2 layers of material. The top one is ablative, that you will be able to withstand very high temperature. And the bottom layer is what you call insulative. And you actually combine this concept and do a dual layer. We are actually picking it up from NASA. NASA Ames has been very using this particular concept to do dual layer. We actually use that in our lab, and we develop these materials in our laboratory. The third and not the last one is what I call low density flexible ablative. And this is something that we have been working on for a number of years. We will actually use a very high char yield resin. It's called UHDL, it's polysiloxane. And we actually use different type of low density felt, ranges from graphite to carbon, PPI, quartz. And that's what we developed actually in our laboratory. We were able to use very small scale in our lab and develop the procedure. And that's what you can see, that we choose a different resin and we use different felt, and we were able to do all these development in our lab. Okay, so we were able to use roughly 6 by 6 inches, and you can see in a steel pan, we will be able to develop the process and fabrication procedure. And these are called low density because it ranged from roughly 0.3 to 0.35 grams per cc. We are moving forward with a new development on needle punch some of these quartz or quartz carbon fabric, and we are actually getting into bigger size, sort of scale up. All right. So those are the three different type of materials we are developing in our laboratory. The next actually area that I'm going to talk about is thermal property characterization. Okay, we actually use TGA, we use MCC, we also use char strength sensors to examine what is the compression and shear char strength of these materials after we expose to oxyacetylene torch. Oh, these are instruments that we actually have to learn more about the materials that we are developing, and we would like to learn the mechanism of why is it working so well. So the next thing I'm going to actually discuss in this seminar is how do we actually measure the char strength? Because char is very important in ablative, and ablative TPS, as well as actually ablative for solid rocket motor. So we were able to develop these instruments in our lab. Okay, so these are actually what I call compression char strength. So we actually have a linear actuator. We will put the materials in here, and we will be able to measure the char strength of the compression char strength. And these are all actually designed and made in by my students at UT. All right. So this is another one that we call shear sensor. And this is actually another sensor that we developed in our lab. We use the same actually data acquisition system, and we actually developed another test stand to measure the char strength. What I'm sharing with you, actually, some of the data that we have been collecting, and these are materials that we have been actually developing for mostly Department of Defense. So this is using Kevlar EPDM. This is a solid rocket motor insulation, and we were able to use small amount of multi-wall carbon material, and we were able to actually see the average energy dissipated. This is how we quantify the strength in compression, as well as like shear. So don't pay too much attention at the numbers. What I'm trying to convey to you is a methodology that we developed to understand why this material is working well. We were able to actually combine and correlate some of these data to performance. And this is what we actually have been doing, okay? Another area that we spend a fair amount of time is to measure the in-situ ablation, recession, and thermal sensor. These are the technology we actually have been developed throughout the years, and these were actually funded by Department of Defense. And we published a fair amount of paper, and you could actually have more detail of these paper after the seminar. Okay, so these are the in situ thermal like ablation sensor that we developed in our lab. And you could see these, we actually use ultrafine thermocouple. These are actually roughly 0.25 millimeter or 250 micron. And we will be able to insert these material, sensor and a different what we call stacker distance from the front, and we were able to collect the data, and it is actually what you're showing. It's one of the material that we received from NASA is the AFCO material, and we were able to do all that. Well, this technology was able to apply to, you could examine the different type of material. We have been using this technology to measure and calculate the recession rate. Take a look at the density. These material ranges from 0.3 grams per cc all the way to these ceramic matrix composite 1.83 grams per cc. Okay, what it means is this technology is very versatile. We're able to actually use it on a variety of TPS material. Okay, so that actually had been published, and we were able to develop this particular technology and use it in our materials development. Okay, so the next area I'm going to actually share with you is aerothermal testing. We done a fair amount of work in this area. We don't just blast material using oxyacetylene test bed, OTB. We also develop photogrammetry, and I go over it a little bit in detail. And we actually use shooting images to understand the flow field. Okay, so this is actually the setup. And if you are around in a UT area, I invite you to come and visit our lab. Okay, but you need to give me some warnings first. This is something that we actually developed at UT. We have a oxyacetylene test bed. We actually photogrammetry that we will be able to measure the in-situ recession during testing, and we were able to actually use two color IR parameter, and we will be able to show you what are the data we are collecting during actually the testing. All right, so this is actually a video that we test MX4926 carbon phenolic at a heat flux of 1,000 watt per cm square. And I'm showing you actually two images. One is we actually test this material, and you can see on the left-hand side, this is how the material respond at these heat fluxes. And on the right-hand side, we will actually have a thermal map of this material during the testing. Okay, these are what I call actually all the data we collected actually during the testing. That's why we were able to understand the morphology, behavior, and the surface, and understand why these materials are working well. Okay, this is actually another slide I'm going to share with you, is that what we are actually using apply this OTB for a dual layer TPS material. Usually these are actually the OTB test condition. We will examine that. We will actually use a Gardner gauge and measure the heat flux. And we have a heat flux versus actually axial location from the OTB. And we will actually use the heat flux and test duration. And we actually, the product of that will calculate ablation parameter. We will actually examine the oxygen acetylene ratio. We will be able to do field rich or field lean. And we standardize our OTB test model to be 30 millimeter. And these are the data we acquire during the testing. And we have been doing this for a number of years. Okay. All right. This is actually what I share with you. Is a glass polysiloxane material exposed to 1,000 watt per cm squared to 20 seconds. The big difference, a glass, you can see all the glass melting. And here is carbon. And this is actually a formulation that we developed. It's a carbon nanocomposite. We actually include some nanomaterials in the UXTR. Okay, so these are the things that we collect during testing, and not just blast the material. Okay, this is actually a summary of what my students have done in comparing carbon UXTO nanocomposite, and on the top you can see these material that before it was tested and actually after it was tested. Then we could see the glass is melting on the surface. Carbon is not. And we actually examine how we bond these two different layers of material. One is the ablative material, one is the insulated material. And we actually use adhesive actually bonding them or compression molding them. There are differences between all of these. All these actually that we have been actually written in technical papers. So if you're interested in that, you should refer to those papers. Okay, this is actually a interesting showing of what we have done using OTB. On the far actually left, you can see high density is roughly 1.41 grams per cc carbon fiber UHTL molding compound before it was tested. In the middle, you can see during the testing, it is a very high heat flux that we are using, 1,500 watt per cm square for 60 seconds. In the very end, on the right-hand side, you actually see the material, how it looks like at the end of the testing. So we were able to use this. This is only a screening test. We are not correlating these results with ArcJet, but if you actually use this kind of methodology to screen your material, you will be able to actually go to the more expensive ArcJet testing or other type of testing that you will be actually required by your sponsor. Okay. So this is actually something that we start developing. It's called photogrammetry. Photogrammetry is a technique that you'll be able to use two camera and you'll be able to map the actually the in situ recession during the testing. Okay, so this is actually what we do with what we call a workflow. We have the test samples and we generate a mesh, and we will be able to use the two camera and use the actually the in situ data we are collecting. And this is what you could see, that we will be able to calculate the in situ recession rate of these materials we tested in our lab. Okay, so this is actually a good example that you could see that you will be able to have surface recession plot, and this is all my students doing. Okay, so this is all the research, and we actually modify this particular actually technique, and we will be able to use this technique in a lot of ablative materials we develop in our lab. Okay, so this is some data that we are collecting on Pika Gen 3, and you can see we actually use different heat fluxes on that we were able to use photogrammetry and calculate the recession, and we were comparing Gen 3 and Gen 2 data, and that's what we are able to see. These kind of data are very reproducible. We receive the Gen 2, Pika Gen 2 and Pika Gen 3 material from Spirit, from FMI, and we work very closely with actually the company. They sent us the material, and we were able to conduct a fair amount of testing. And this is actually a comparison actually showing you why we actually use different heat fluxes to see, can we use photogrammetry and measure the actual recession and compare with experimental recession. Experimental recession is basically what you measure before and after. Photogrammetry is actually in situ. We were able to do all these, and we were able to calculate actually the standard deviation, and the error that we see is very small, 13%. Okay, all of these are actually, we were able to do that. So we actually have a map of the different type of materials we are now collecting. And my student actually is going to present some of these results in AIAA Science Tech in January in Orlando. Okay, these are the different type of material we start collecting using photogrammetry in our lab. Okay, this is something that one of my PhD students did in understanding the imaging using string, the A, B, and C. A basically is where we are looking at laminar flow. B, that we will trigger it in the turbulent flow. And C is what we are actually measuring using OTB, using a very low heat flux, 1,500 watt per cm square. And D is when we push to very high heat fluxes. You can see the flow field is very different when you actually have the OTB impinge on the ablative material. We are also linking with some of these CFD model that developed in our group, that these data will be able to help us to actually validate our OTB like CFD model. Okay, so I'm going to go over the thermal, physical, and mechanical property characterization. This is very important because if you develop material, you test them, you really need to know the thermal physical property as well as the mechanical property. And I'm just showing you some. These are very detailed measurement, and we will have to do it for each material. Certain materials, we already have these data. Okay, the two materials, we have these data. It's pica and carbon phenolic. We have to measure. We don't do that. Okay, we actually have to send it to another laboratory to do that. It's Kratos. They do a fair amount of all these thermal physical property, virgin property, and a whole bunch of these parameters and the pyrolysis properties, char property, surface radiation properties. And all of these are actually required to do material response modeling. Okay, this is something that is urgently needed, and we are now slowly actually characterizing some of the newer material. All these are what we call like thermophysical property. It's required in all these very detailed materials response model. That's why I highlight this. These thermophysical property are urgently needed in new materials for TPS as well as Syracuse. Not just the mechanical property, not just the thermophysical property. We are now actually doing the mechanical property, as well as now we are starting to use the Lawrence Berkeley advanced light source facility in Berkeley, and we will be able to do micro CT as well as we work with University of Southampton. We will be able to do these measurements at room temperature as well as elevated temperature in Berkeley. Okay, so what I'm sharing with you is something that is new, that we are now characterizing only a handful of property. These are the property we need to characterize. What I'm showing you is a virgin and a char specific heat, and this is actually with a function of actually temperature, and this is the virgin actually and the char, and we also measure the thermophysical property with respect to temperature for actually virgin and char. These are non-existent. Only pica or actually carbon phenolic that has been characterized by Department of Defense, and these are required to actually do material response modeling. And we are now starting to say, can we use a small amount of property? Can we fit these properties into the model? How good are the material response modeling? And this is actually one of my master student, Kaylin, that she finished that, and this will be actually presented in AIAA in January. Okay, so the next thing I'm going to talk about is microstructure characterization and modeling. We have published a fair amount of these actually in the open literature. These are the microstructure using SEM. SEM has been used to understand the microstructure, and I'm showing you the virgin material. Pica is a carbon phenolic material, and it has been around, and it was actually developed by NASA Ames, and my student will actually do SEM of the virgin material. And when you examine the char, the resin, the phenolic resin is all polarized, and these are all carbon fibers coming actually onto the surface. These are surface methodology. Okay, so 2022, we start going to Lawrence Berkeley Lab Advanced Light Source, and we were using actually beam 8.3.2 This facility is phenomenal. We were able to perform micro CT computed tomography of various fiber form that actually use in ablative composite. We will examine the virgin material, we will examine the char, and we already examined some of these pyrolysis and mechanical property at room temperature and later on elevated temperature. This is like a phenomenal facility. Okay, this is actually a a micro. You'll be using hard X-ray, micro CT, and you will be able to do 2D scan and use software to reconstruct a 3D structure. That will give us a lot of insight of the material's behavior. Okay, SCM, you could only do 2D. Okay, like micro CD, you could do 3D. Okay, what I'm showing you is we actually have to use a Dragonfly software, and majority of the other university and laboratory have been using Dragonfly to actually reconstruct the 2D images into 3D images. We were able to have done 3 series of micro CD experiment at Berkeley, and majority of them will be published in the open literature. What I'm sharing with you is a 3D construction of a carbon phenolic. We have all these 2D structures, and we actually will use Dragonfly and actually reconstruct a 3D. What I'm sharing with you is this is actually a like MX4926 that if we actually use the 3D microstructure, we could understand the materials a lot better, and it will provide us with insight. These are very useful tools that people have been using. Now we're starting to use it on traditional material as well as new materials that we are developing. Okay, so this is actually a still 2D that you will compare the virgin glass phenolic versus a char glass phenolic. You can see the big differences in the morphology of these material. Okay, so this is something that we start examine high density quartz fiber, and what you see on the left hand side, this is actually a quartz fiber that we actually received from Singapore, and we were able to use micro CT in Berkeley, and we will be able to generate actually 3D structures. On the right hand side, you could see a virgin quartz infiltrated with polysiloxane, and you could see all these particles of UHDL in the material. So see on the left-hand side, you can see just a scan of the quartz. And the right-hand side, you can see how the resin infiltrate into that particular quartz fiber. And this is what you could see in a virgin. What is that for carbon UHDL versus the char? Because you could see from the virgin, a fair amount of this UHDL resin is still stick on the fiber, but as soon as you expose to an OTB at certain heat fluxes, the resin is going to polarize. These kind of understanding will help us to have better insight of why the materials behaving so well. This is what I call actually the mechanism of why these materials we're developing. Okay, using the micro CT and a software developed at NASA Ames called Puma, and we'll be able to calculate some of these properties. Okay, that's what we actually are now using the micro CT data and this particular software to provide us with some of the properties that we are interested in based on micro CT data. Okay, this is something that we are working with photostate, that they were able to measure the thermal conductivity using their actually the C-firm system, and we were able to measure the char, the virgin, and the char of some material that we're developing. This is actually a graphite UHTL. This is another graphite UHTL. The third one is quartz UHTL. We were able to measure these we send the materials to photostate, and instantly they actually have an excellent, actually high performance, actually MI, actually laboratory in photostate. Okay, so we were able to measure these, the thermophysical property of these material that we are developing, and we were able to measure through the thickness. And in order to calculate some of these, we have to measure the thermal properties of the virgin of also of the fibers, and we will actually provide actually the thermal conductivity measurement was done at photostate, and the fiber were actually we were using the technical data sheet from the fiber manufacturer. We're able to do all these and actually fit all these properties into the software. The Puma software will be able to calculate and provide you with actually properties using actually deep learning segmentation model, and we'll be able to calculate some of these thermophysical properties through the thickness. And this is what we have been doing, okay? And this actually software will be able to calculate at the X, Y, and Z. See, for the experimental, we were only measuring through the thickness, which is the Z direction, okay? We are not able yet to measure the X, Y, but with these actually micro CT data with the software, we may be able to actually provide you with a lot more insight of the material, thermal conductivity, and other properties that you'll be calculating. But we always use experimental data to validate our model. That's why we are using thermal conductivity. Okay, so these are the experimental data that we receive from photostate, and these are calculated. They are actually okay. We are now examining what are the differences, but at least you know that these modeling is good enough to provide you order of magnitude, not totally out of line. We're able to do these measurements, and these were reasonable. And that's why we are now examining how can we make it better. But the important thing is we'll give you a guideline of what you can do with the modeling and with the thermophysical, actually thermal conductivity. But the modeling actually will give you more information. Some of these are actually we cannot measure. All right. So that's why we are actually using experimental methods provide us with these data as input to material, actually to the like microstructure modeling. Okay, so the last not the least piece I would like to share with you was materials modeling. Well, actually this is an area that we are now exploring, and we actually use a fair amount of computer code that has been used by NASA as well as Department of Defense and Northrop Grumman, that they use these computer code that we were privileged to have these computer code. My student will be able to calculate some of these actually like pre-prime table and other things that we need in order to calculate the materials response model. Okay, this is something that we are working on using actually Fluent to calculate what is the direct jet impingement, what are the like flow field that we could calculate. These flow field parameters, we have to set it back into the materials response model. And that's what we are now simulating the CFD flow field with our OTP. Okay, so this is something that we have been doing. We have been actually doing experimental preheat fluxes. This one is 250, this one's 500, and the last one is 750. These are actually condition that we test, and this is the pica material that we were able to measure. These are all experimental data that we are collecting with a variety of heat fluxes. These are actually standard heat flux that we test in our lab. Okay, we are using pica material, and this is actually open literature. You'll be able to see how this material behave in these kind of actually condition. Okay, so the next thing we do is we use machine learning, and we use a 1D Fiat, which is a program that you will be able to obtain from NASA Ames, and we will form a material response model, and we will actually use that along with the property that I just explained, the thermophysical property, and use the OTP experimental data and provide us with a material response model. What you're seeing here is actually how the calculated versus the experimental data, and this is what we're doing with different heat fluxes. These my students actually have been published. Okay, so that's the one that I'm very excited is the new materials we are now developing, and the new thermophysical property that we actually ask a third-party lab to provide us, and we were using limited thermophysical property, and we formulate a materials response model using 1D Fiat, and these are what we comparing for modeling and experimental. It is actually not too bad when you examine these at different heat fluxes. This one is the lower heat flux of 500 watts per cm square, and my student actually have done 500, 1,000, and 1,500. This actually will be presented in AIAA actually in the science tab in January. Okay, so what we have done, I'm going to summarize. I have gone through a lot of things and a lot of capability. I want to actually summarize it. What we did is we actually developed a several integrated, what I call integrated is not all these actually technical capability we developed within the COOL research group. We use that to analyze TPS material. We are now using some of those for solid rocket motor. We were able to demonstrate throughout the year using in-situ ablation and thermal sensor on a variety of TPS material. We validate some of these models using the 1D computer code, 1D Fiat, CMA 93, and iTrack. It's actually a computer code from Northrop Grumman. We also plan on using another actually computer code is called CAMAX that's developed at actually Northrop Grumman to calculate the B prime table. And can we actually use the new development and use our experimental, and eventually we'll develop materials response model using a more sophisticated actually computer code 3D char from NASA and Hero 4 from Northrop Grumman. I think these are the computer codes that's available in US. Probably in Europe, they have another set of computer code they were using in actually in Germany or maybe actually in France. Okay, so what we did is we conducted over 100 preformed virgin and char actually of these materials in Berkeley. And we are also sending some of this material University of Southampton. We were using actually NASA and Puma and calculate all these materials property that some of them we were not able to measure, but we are actually using experimental data to validate these model. And we already did some tests, actually micro CD actually experiment in Berkeley. We will examine pyrolysis of neat system, low density, flexible, and medium density ablator, and we were able to actually doing mechanical product, mostly compression, and we're analyzing it. I think we were originally using a workstation. Now we need to actually have to go to use the UT supercomputer in order to calculate some of these property. We were able to what I call use optical advanced diagnostics. And these are what we call low cost. These are all ground testing. We would like to extend the thermophysical property at TPRL, Kratos, and actually NASA Ames. They have this capability. We will be able to apply them and use these properties apply into material response model. And my goal is to examine the new material. We are now actually using the char sense strength data. We would like to link the char strength with the performance of these material. And we find out this actually equipment is very useful for learning the char strength. And all these things that we try to do is eventually with more data to validate our material response model, as well as the Puma model using additional OTB, ICP, all these data, okay? The goal is actually to develop a process, property, performance relationship with all these new material, okay? I think everybody is trying to do the same thing, is to couple aerothermal ablation, actually shape changes with some of these actually simulation tools for TPS development. I think besides actually developing actually the modeling, we are also further develop these material in the low density, and we find out that we could needle punch some of the quartz or quartz carbon fabric, and we were able to actually make bigger sample and improve our actually fabrication technique. The last not the least, I would like to acknowledge all our funding agents from Department of Defense, NASA, and some of the private company. And I also would like to thank my current and former students to contribute this research, the folks from NASA, Johnson, and the folks from NASA Ames helping us, as well as Norfolk Grumman helping us. The last, not the least, we have been very appreciative with Dr. Parkinson from Berkeley to teach us how to use these actually micro CT, and also now we are collaborating with University of Southampton to characterize the microstructure, as well as Matt from NRL helping us to grind some of these polysiloxane material to do our other development. These are the current actually members in our research group, and this is what I actually have been teaching at UT, polymer nanocomposite. That's kind of my expertise, and this is the book that I have been putting together for published by Cambridge sometime next year. I think the last one I would like to plant a seed to all the different attendees is contribute to SAMP Journal, and we actually is trying to, I serve as actually the North American regional. I would like you to submit paper to the journal to bring our impact factor higher. And I think that's what I would like to start. With that, I'm ready to answer questions. Robert, am I doing okay with time? Robert? Robert,
I'm here.
turn it on. Okay. I've gone through a lot of materials in a hurry, but the most important thing is share with you how we solve a problem. That's all. Okay. Go ahead, Robert.
If anyone has any questions, please put them in the Q&A, and we will get them answered. I'll start off with a question. So processing and fiber architecture are going to be very important in ablation. Can you, you've shown different felts and needle punching. There's also, a 2D laminate or a random oriented chop fiber, and then the gold standard of a 3D woven. Can you comment a little bit on that?
Well, 3D woven is the gold standard. It's very expensive. Not too many people could afford to use 3D woven. Okay. As a matter of fact, only NASA would actually have been using 3D woven. But the 2D actually different materials I would like to address that is phenolic is the gold standard. We have been using phenolic for more than 100 years. And my question is phenolic the best material? It's not. Throughout all these years, we need to examine the different high char yield resin system, and we need to push these new materials into the community. Carbon has been used a fair amount. Can we actually use like other reinforcement, not just the type of reinforcement? How about the architecture? That's why we are now examining in some of our current study, we are using low density. We are comparing with Pica. Pica is a carbon infiltrated phenolic, but we are actually changing the fiber using quartz and using carbon PBI. And those are the new things that we will make the new materials to be better. But most important thing I want to actually point out is these are very cost-effective material. And if you try to do 3D woven, it's not very cost-effective. Enough said. Okay, Robert.
One of the Q&A questions is, will the thermal degradation mechanism behave similarly in epoxy-based carbon prepreg composites?
No, it is not. Do not use epoxy for TPS. All right. Epoxy is not the material you should be actually examined for TPS, thermal protection system. Carbon phenolic is the gold standard, and you have been seeing that starting in the 60s. Okay, so the mechanism of all these resin systems that we has been examining are very, very different. That's why we are actually studying some of those, and the micro CT is going to help us to understand certain of these mechanisms. Okay.
The next question is about carbon nanotubes. So the question is about when you get to high weight percent, such as 10%, you get a very high viscosity. And how do you work with this, with the resins?
Well, that is actually one of my expertise on nanocomposite. Go read my book, but I want to actually stress that is this. Yes, nano materials, you do not need to put, the rule of thumb, I always say 5%. You shouldn't be actually putting so much nanomaterials, and it's not a nanocomposite anymore because you need to examine actually the dispersion, and you find out that when you put so much, now the question is, can you put 10 weight percent CNT in there? You're wasting your money. You shouldn't be using actually 10 weight percent of CNT into your resin system. You need to see how well it's dispersed, and that is very important. Okay, thank you.
There's a couple questions about materials. One's about borate in the ablative materials. Another one is about experience with cyanide ester.
Good question. I start hearing about boron, but I actually do not actually have personal experience with that. But we actually have actually written a fair amount of review paper. Two of them actually have been published. The third one we are trying to publish that reveal what other people all over the world has been examined. Boron, there are some people have been using that. I personally have not used it. What is the next question, Robert?
Um, there's one in here about cyanide ester resins and
Oh,
also
cyanide ester. I actually used cyanide ester a long time ago. I want to point out, you need to examine the char yield. Cyanide ester do not have a very high char yield. Okay, char yield is a definition that a lot of people use, but every researcher used a different uh, definition, so you cannot actually compare using the literature. So what we did is, in our group, we will solicit a lot of commercial available material, and we use the same definition for char yield, which we have 20 C per minute in nitrogen. And when you heat it up to 1000 degrees C, that the vast mass remaining is the char yield. Cyanide ester in our lab has not been what I call a high char yield actually resin compared with phenolic and other resin system. Thank you.
the last question is just about any alternative resins and fibers that you kind of see in the emerging
Yeah.
in the market.
Like I said, there's a whole bunch of resin system, what we call high temperature system. We actually have some proprietary data that we compare with all of that. We have not published some of those, but like phenylitride, PN is very good. The polysiloxane system, we have done a fair amount of work, and that has been very high char yield. We don't just use carbon. Okay, carbon is extremely good. I think I start learning about there are different type of carbon. There are pen fiber. There are also rayon carbon fiber. So we examine some of these, not just the carbon type. We also examine the architecture. That's what we are now studying quartz, and we work exclusively with Saint-Gobain because Saint-Gobain has been very generous to providing different type of actually quartz fiber and architect into our lab. We are now combining some of these, and you examine the literature. People have been combining carbon and quartz. They are also show promise. But I always say that, can we actually do it with an industrial group? That's what I'm always working with industrial group, not just say, we could do a few things in my lab. Okay? All right, Robert.
Well, I think that concludes the webinar. I think we're out of time. We really appreciate you, Dr. Koo, spreading your knowledge to everybody in the SAMPE community.
You could always send me email or actually send it through actually to Robert or Raj. I will answer email selectively. Thank you very much.
Thank you. Don't forget the survey, please. Thank you, everyone.
Thank you for all your attention. Have a great day. Bye-bye.